This is Lab 2, Motion of a Falling Object. The purpose of this lab was to observe the effects of drag and falling motion. During this lab, we used the tracker program to observe the motion of an object in freefall. These results were compared to computational models of the same motion using the same initial data as the observed model. Two different computational models were used for this comparison. One was a model accounting for only the effect of gravitational force, and the other was a model including both the effects of gravitational force and drag force. The fundamental principles involved in this lab were derived from Newton's second law and the definition of net force, which is the sum of forces acting on the system. Also, we know that the drag force acts in the opposite direction of motion for this lab. The results of the methods you will see in the following slides show that the computational model with drag and the observational model using tracker were similar but not quite the same. We'll explain this in later slides. The computational model without drag increased in velocity at a much higher rate and as a result changed positions towards the negative y direction at a much higher rate. And no matter if the object were thrown or dropped, it still reaches the same terminal velocity. This is the observed motion using the tracker system. This is the predicted motion, the computational models. Now this accounts for drag. This is a visual comparison of the models observational, computational with drag, and computational without drag. As you can see, the computational without drag goes farther and at a faster rate because it isn't slowed down by the effects of the drag force. Now I'm going to analyze each of the parts individually. For the computational model with drag compared to the observational model, we can see that the forces acting on the object are the gravitational force exerted by the Earth and the drag force. Together, those equal the net force. The drag force, however, is acting in the opposite direction of the gravitational force. The drag force is acting in the positive y direction, and the gravitational force is acting in the negative y direction. The observational model is similar, but not exactly the same as the computational model. The forces acting on the object here are assumed as the same as the computational model with drag to be the gravitational force exerted by the Earth and the drag force. However, there are other forces we can't determine acting on the object, mainly because the falling object was a piece of paper, a postcard, and the fluctuations in the way that the air hit the paper could have caused the waviness here and the fluctuations between the observational model and the computational model. However, here the same, we know that the drag force acts in the opposite direction of the gravitational force. Comparing these two models that incorporated the drag force to the computational model that didn't incorporate the drag force, where the only force is the gravitational force exerted by the Earth on the object, we can see that when there is drag, the net force is going to be smaller than if there isn't drag, which means that without drag, the velocity is going to increase at a faster rate. Terminal velocity is the highest velocity attainable by an object as it falls. This occurs when the drag force equals the gravitational force, and as a result, the net force becomes zero. Here in this position versus time graph, we compare our two models from before, the computational model with drag and the observational model, with a computational model of an object, the same object, but if it were thrown. This is a graph of the same model, but a velocity versus time graph. So here we compare the computational model with drag, the observational model, and the thrown model. So we can see that these three lines are converging at a singular point, which is the terminal velocity, and we know that if this graph went further on, we could see that all three of them achieve the same terminal velocity, even if they achieve it at different times.